Okay, so now moving on, we will approach two discrete and two continuous variables, more concretely cross tables and correlations. So now I will approach cross tables. The hypotheses that we will be tested in cross tables are more complex to write, so I will just say that we are testing independence of variables, as you can imagine. There's a specific tweak if you are working with dichotomous variables that you can fix the group 1 versus the group 2 as different, higher or lower, but this only happens or is available with dichotomous variables. So we need two discrete variables or two or more groups per variable. The priors, now this is different from t-test, and it's pretty interesting because there's a more diversity. Okay, so one of the priors is a Poisson distribution because it has not any restriction in the cells and total sample size, so it's very flexible. So each cell of the cross table will hold a Poisson distribution that you can specify the parameter if you want. You can also have a joint multimodal distribution that you need to have a fixed total sample size that you need to specify. You can also have independent multinomial distributions, fixing the rows to 50% each, or columns. This is the priors that you will need if you have dichotomous variables with that trick that I described earlier. And also you can have an hypergeometric distributions that rows and columns are fixed at 50%. And one of the examples that this works is when you have median split continuous variables and you need to do a cross table or something like that. But maybe there can be some cases that you need this. Okay, so whatever you choose as the prior, you can specify the prior concentration parameter. This is basically the informativeness of the prior. The default is 1, but you can increase it. So the results will be a Bayes factor, also the cross table with the percentages and frequencies if you want. And also, if you have a 2 times 2 table, you can have a prior and posterior plot with the credible intervals and maximums, okay? So here is a non-informative prior. As you can see here, we have having a previous injury and gender. Here are frequencies. We can also ask just for the percentages by column, by row, or by total sample. Here is the Bayes factor. And here is the prior posterior with the log odds ratio, the Bayes factors for 0, 1, and 1, 0, the median for this test, and the credible interval. Okay. Here's an example with a one-tail ratio, log odds ratio, and non-informative prior, a one-tail test, because here the alternative hypothesis is that female is going to be greater than male. Okay, so this is the test that we are going for. And now it's the log odds ratio needs to be positive, a bit above 0, and therefore the plot changes, okay, and the Bayes factor changes. And here's the example with the left-sided test, okay. As you can see here, was the results change. Okay, so as you can see here, cross tables can be very complex, and regarding Bayesian inference can also be very complex. So you need to have much care regarding what distribution do you want for the prior. If you want an informative prior, which value do you want? And also the Bayes factor that you need to interpret needs to take into account that distribution that you're using. And if you want to have a one-tail test or a two-tail test, that is also important. Okay, so now that we have two variables, I will address the case of having two continuous variables, and that means basically Bayesian correlations. Okay, so Bayesian correlations have an effect size that is going to be tested. That is the population correlation. That can be two-tailed or one-tailed, as you can imagine. We need two continuous variables with a linear relationship between each other, desirably to be normally distributed and also without outliers. And now we can have a different set of priors. Non-informative priors are a beta distribution with beta equals 1 as the default. And also we can become informative if we just start to modify alpha, okay? The informative distribution or the informative prior is also a beta distribution. However, we can decrease or increase our beta parameter, okay? So we will have a Bayes factor, the distribution of the prior and posterior, and the posterior maximum with the credible interval. They will also have the 3-star system implemented here, I suppose because JASP team was assuming that a lot of people are going to look at the correlation matrices. So to be quick and to decide which is significant or not, remember here we don't have any statistical significance test. It is set, this 3-star system, as Bayes factor above 1, above 10, and above 100, okay? We will also have the sample correlation, the credible interval, and optionally we can have some scatter plots, and also we can opt for a robustness and sequential analysis. Okay, so here is a two-tailed correlation test with non-informative priors, and you can see here that we have the Pearson correlation, the Bayes factor of 0 plus. This is a test regarding correlations with a credible interval, and now we have this plot that I think is pretty neat because we have the histograms of both variables. We have the scatter plot here, and also this is the density of the posterior, which is, I think, is pretty informative because in one single shot you can have the whole information regarding normality, linearity, outliers, and also how the posterior is working right now. Okay, so here is also a two-tailed non-informative prior without the correlation matrix outlook. And now we will have only one specific pair, one specific correlation, and now we will specify that as Bayes factor 0, 1. As you can see here, we have this Bayes factor. Now we will have a prior posterior plot. This is the prior. As you can see here, alpha equals 1 and beta equals 1 produce a flat distribution, but as you may increase or decrease beta, the form will be different. So the posterior indicates basically 0 correlation, as you can see here, with the credible interval that is pretty large because we have a very small sample. Here is the scatter plot with the line, and now we have here a robustness analysis. As you can see here, if we chose less informative prior, the Bayes factor will increase in general, okay? And as more informative prior we will have, it will decrease. And here we have a sequential analysis. As you can see here, we have also dots, not lines, and we don't have the robustness check here. That is this way of making the sequential analysis to have different levels of prior width or stretched beta prior width. Okay, so we only have our chosen estimate. Okay, here's an example with a one-tail distribution and one-tail test truncated to be positive. Here we have a 0 plus Bayes factor. Here is the robustness analysis and the sequential analysis. As you can see here, we have more or less the same outcome. It's not very robust because the situation will change significantly as long as we choose a different prior. However, in the sequential analysis, we can see here a general pattern towards supporting H1. Therefore, it is, no, not supporting H1, it's supporting H0. And therefore, maybe with new data or with more data, we can make a more informed inference. Okay, so here is an example of a two-tailed test with an informed or informative prior. Okay, so beta right now is equal to 2. And now, as you can see here, the prior is becoming different because we have a two-tailed test, and because of the beta right now is higher, right now the shape, as you can see here, is more likely to become in extreme values because we are betting on having different from 0 correlation, okay? However, as you can see here, the data likelihood is still supports heavily to be around 0, and we have also the robustness check, the robustness analysis, excuse me, and the sequential analysis, okay? So here's an example of how you can modify the prior to get a different Bayes factor, okay? Okay, so here is also an informative prior, a very informative prior with beta. Instead of having a greater value that is far from 0, it's going to be around 0. As you can see here, we have a beta of 0.001. The prior and the posterior are basically indistinguishable because they have basically the same shape. And so the data just supports this degree of belief that the correlation should be 0. And we have here now we have a bias factor 0.1 of 1.07, so it's basically inconclusive evidence supporting H0 or H1. As you can see here, the sequential analysis is basically rounding around 1. So the bias factor says that the two models are basically the same, and we still have the descriptive data. So as you can see here, probably the true correlation, because we have so little data, we don't know with more strength a conclusion on the parameter. However, you can see here that the relationship between box office and freshness of the this is a database of Adam Sandler movies. The freshness is the critics receive on Rotten Tomatoes, and here is the box office. So as you can see here, they are pretty much independent. Okay. If we have problems with linearity, or we have problems with normality or any kind of assumptions, we can choose to have non-parametric alternative. We don't have the Spearman correlations available. We have the Kendall correlations available, the tau B Kendall. So as you can see here, it will be calculated with its own bias factor. Here is the prior posterior for this choosing. And we can have also this kind of plot and also this kind of plots. Okay, so as you can see here, cross tables and correlations from a Bayesian point of view can be kind of complex, but if you know the basics, which is the prior, which is the posterior, if we can check the difference between prior and posterior, how the prior can be changed in the parameters, what is the bias factor. The bias factor is put as 1, 0 or plus 0 or minus 0 or on the other way around. Because they indicate different things, and also how to interpret a robustness analysis and also a sequential analysis. Okay, so this is basically the main bivariate test that we can take, making a Bayesian inference.